So we've seen how a discontinuity can be dealt with Laplace transforms. The Heaviside function was a discontinuity of the type of suddenly something being turned on. We now want to start talking about a function that it sort of represents or models a sudden impulse, a sudden short-lived impulse. Okay, so it's going to be called the delta function, but let's work up to that. Let me start with a function that looks as follows. So let me put a 3 here, 2, 4, and let me put a 1 here. And imagine a function that is 0, and then at 2 it goes up to a half, and then at 4 it comes back down to 0. Of course, maybe I should put dotted lines here and here, right? So let me write that function out, and I'm going to call it g1 of t, and it's simply 1/2 on the interval 2 to 4, and it's 0 otherwise. Okay, fair enough. So think of that as an impulse, but this one's not too short-lived. This lasts for 2 full, time units, 2 full seconds, and its strength is 1/2. Okay. Now, let's now move to a function that looks as follows. Let's have it be 0, and then at 2.5 it goes up to 1 until 3.5 and comes back down. So let's call this g1/2. Let's label the function as that. So it's 1 from 2.5 to 3.5, and it's 0 otherwise. Okay. And what I want to point out is that, from a modeling standpoint, from the standpoint of if this is a force that is applied to something, these two in a way have roughly the same effect, because this one is twice as long but half as strong. The force was equal to 1/2 but for 2 full seconds, whereas this one was equal to a full 1 but for only 1 second. And in a way, sort of the strength of an impulse, of a force applied over a period of time, is both have to be taken into account. It's the strength times the length of time that it lasts. In particular, it's the area. And so both of these have an area of 1. And if you've had physics, that actually literally is in physics called the impulse. It's the force times the time. That's called the impulse. From a calculus standpoint, I'm saying it's the area, but of course we also know that what we're talking about is the integral. So I'm saying the integral of this function is 1. The integral of this function is also 1. Now I'm saying integral, but I didn't put limits. Of course, it kind of doesn't matter. I can just go minus infinity to infinity because it's 0 most of the time anyway. So for this function, minus infinity to infinity really means 2 to 4. And for this function, minus infinity to infinity really means 2.5 to 3.5 because the rest isn't contributing anyway. Okay. So two functions that kind of have the same impulse of 1. Now, I can keep doing this. I can keep making smaller time intervals, but stronger magnitudes of force, such that it still has an area of 1. Okay, so as the most general case, you can imagine something goes 0, and then right before 3, it spikes up to a very high number, and then comes back down like that. And so we can imagine that from 3 to there is delta t, and also from the left-hand side to 3 is also another delta t. So the total amount of time is 2 delta t. And the height of the function is 1 over 2 delta t. So that, this would be a rectangle that's 2 delta t in width and 1 over 2 delta t in height. So again, it would have an area of 1. again, the integral of this function, and I'm going to call it g delta t dt is still 1. Now, just to be specific, g delta t of t is, so it would be 1 over 2 delta t on the interval of t from, it would be, and sorry, I didn't leave enough room, 3 minus delta t to 3 plus delta t, and 0 otherwise. So that would be the function. And it's lasting less time, but much stronger while it is sort of turned on. But it still has sort of the same effect, and that's the point. And so we realize that maybe in a lot of applications, these three situations are all going to pretty much amount to the same thing overall, sort of the net effect. It's the same impulse. So why don't we propose, in order to model a really, really short and really but strong while it's lasting impulse, a really short-lived one, why don't we just take this to the limit? And so that would look like delta t smaller, smaller, smaller. So this function is 0 everywhere except 3. And at 3, it's basically at infinity. And this function is called delta. And in my g functions, I didn't indicate the 3. But I will now. The delta, I'll put a subscript of 3 to indicate that this impulse is happening at time 3. Okay, and it's 0 everywhere except 3, but somehow it's infinity at 3. But what we wanted to say is that it's sort of the limit of the functions above. So we want to say that delta 3 of t is the limit as delta t went to 0 of g delta t of t. So skinnier, 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 taller, taller, taller. This is what the function would look like in that limit. And so since all along, all three of these had the same integral, of course we would say then that that wouldn't change when we get to the limit. So the integral of this function is 1. And that's the delta function. Specifically, it's called the Dirac delta function. It's named after a physicist, Paul Dirac, who used this notation for this idea. And essentially, let me just say that, we could be more realistic, I guess, and exact in our model, and model a really quick impulse, a really quick hit. Maybe we actually use one of these g delta t's with a delta t of 0.01 seconds or something like that. We could estimate the amount of time that this really quick whack takes place, and actually use the real function. But that would get messy a lot of times, and it wouldn't be too different from this conceptual function, this delta function, which we're just to simplify things, we're not going to deal with little 0.01 amounts of time. We're just going to go with a function that is sort of instantaneous, and it's going to turn out that we can do lots of the math just as well. In fact, it'll be easier because we won't have lots of sort of arbitrary 0.01 seconds floating around. We just treat the impulse as instantaneous. Now, I know what you're thinking. Technically, this is not a function. But we're going to treat it as one anyway. And this can be made more rigorous, but we don't have to do that. We're just going to treat it as a function anyway. It's not a function because, of course, infinity is not a real thing. It's not a number that a regular real valued function can equal. So you're not supposed to get infinity out of a function. It can be the limit of a function, but it's not supposed to be the actual answer to a function. And of course, this also is not 100% legitimate if we're following the letter of the law. Because in what real sense are we saying that the area under this function is 1? It's got 0 width, but it's got infinite height. So who's to say what that is? It's sort of like a 0 times infinity situation. But like I said, we're treating it as the limiting case of this sequence of functions. And since these all had the property that their integral was 1, we're going to say this guy, this conceptual function, has an integral of 1. So we're just going to roll with it. We're just going to go with this as a function, even though technically speaking it's not a function, but it's going to produce answers for us going forward. So it's worth doing. And like I said, once we're used to it, it's simpler than being maybe a little bit more realistic and using a g delta t with a really small delta t that we sort of arbitrarily estimated. All right. So sorry, I should write this in. This is called the dirac delta function, or a dirac delta function. Sub 3, of course, we can move that point around. We could have a delta 2, and that would be an impulse here. We can have a delta function at any given point. Okay. Now, the delta function has a nice little property that I want to get to, and in order to show this to you, I need to bring something back from Calc 1, and it might not have been emphasized too much in your Calc 1 course, so it's possible you might not even have seen it, but it is sort of at a Calc 1 level, and I'll just quickly describe it, and then we'll use it going forward. If you want to figure out the average value of a function, so of course with discrete numbers, right, if we have a bunch of discrete numbers, right, if we want the average, what we do is of course we add them up and we divide by how many there are. Easy. So that's what we do when we have a discrete set of numbers. But if we have a function, okay, you can think of this as really infinitely many values, infinitely many numbers, right? Between, let's say, between two endpoints A and B, f is a bunch of different y values. And it seems like it should make sense for us to ask, what is the average value of f between A and B, right? Some sort of intermediate value that, sometimes this function is lower, sometimes this function is higher, but on average it's one number. We should be able to figure out the average value of a function. And we can. And what we define it to be, or what it turns out is the right way to define it to be, is, well, we follow this pattern, we follow this model, and just sort of go to the continuous version of it. The continuous version of adding up a bunch of numbers, I think you would know, is integrating, right? An integral is adding up all these values. So integral of f of x dx from a to b, that's the analogous thing to adding up all its values. You integrate up all its values. Now, what's the corresponding thing to dividing by how many there are? Well, we don't want to literally do that because, of course, there's infinitely many values between a and b. So we don't want to divide by infinity. But it turns out that the right thing to do is to divide by the length of the interval. That's sort of analogous to like how many values we're including. So divide it by b minus a. Okay, so more often it would be written like this: 1 over b minus a times the integral. Okay, so that's the, and sorry, I should not write I should not write a line over x now. I should write the line over f of x is the average value of f of x. Okay, so this is the average value of a function. And it works, and it gives you answers. Like if you put a constant function in, obviously the average value of a constant function will be that constant, and that comes out of this. And like if you had a linear function that goes straight up steadily, then the average value is going to be right in the middle. Like this definition gives all the answers that you would expect something called the average to give you. So it's a good definition. Okay, well, how do I apply this to what we were just talking about? Well, what's the average value of the g delta t function? Sorry, scratch that. Ignore that. Let me start over. Let me start that sentence over. If we want to figure out the average value of some function, right? So what we said was you integrate the function, and then it's times 1 over the length of that function. Okay, so now on the previous page I just did a to b, and then this was b minus a. But let me just relabel things for a second, and let's say that we want to, instead of going from a to b, let me change that, and let's have, like I said before, let's put 3 in the middle, and then we'll have 3 minus delta t and 3 plus delta t. Okay, so now replacing a and b, 3 minus delta t is my a, and 3 plus delta t is my b. So the integral is from 3 minus delta t, 3 plus delta t, and the width of the integral is 2 delta t. Now I'm going to do the following. I'm going to do two things. I'm going to bring that, this is just a constant, so I can bring it in and out of an integral at will. So 1 over 2 delta t, f of t, dt, 3 minus delta t, 3 plus delta t. And now what I'm going to do is I'm going to replace, so how to say this? This is 1 over 2 delta t from 3 minus delta t to 3 plus delta t, okay, and then times f of t. If I replace that with the g delta t of t function, it's the same thing, right? Because g delta t, on this interval, g delta t is equal to this number. That's what it is. It's just this function happens to be 0 elsewhere, but it's equal to 1 over 2 delta t on that interval. So this function and this function are the same thing, and they can be replaced within this integral. Okay. And now what I'm going to do is I'm just going to say, well, since this function, now that I've written it as g delta t, I don't have to be careful about my endpoints. I can just integrate from minus infinity to infinity, because this function zeroes everything out there anyway. It's not contributing to the integral. Okay, so it turns out that another way to write the average value of a function is to use these g delta t functions inside the integral with it, and then you don't have to be careful. You can just integrate from minus infinity to infinity, because the g function kind of takes care of where to start and where to end, because it's 0 outside of that interval anyway. Okay, so this integral will give you the average value of this function on that interval. Okay, well that's great. Now let's turn that into the delta. So remember, the delta function is this g function, but we let the delta t go smaller and smaller and smaller, so that this gets closer and this gets closer. All right, so therefore what I'm going to say is it must be that if I replace g delta t with the little delta function at 3, what I should get is, well, I should get the average value of f of t. Let me write that out in words. Average value of f of t. But on what interval? Well, from 3 minus delta t to 3 plus delta t, right? But in changing the g to the delta, that delta t got smaller and smaller and smaller and went to 0. So this goes to 0 and this goes to 0. So what interval am I really talking about? Well, I'm sort of talking about an interval of no width. It shrunk all the way down to just 3. We'll write it like this, maybe. T is between 3 and 3. That's a really dumb way of saying t equals 3, right? So this integral is giving me the average value of f of t basically at one point. Well, if we're down to 1 point, you don't even have to say average value anymore. There really is only one value, right? So we're getting f of 3. We're getting the value at that point. So that's really neat. So, okay, you followed that, you didn't follow that, it's fine. Hopefully you follow a little bit of it, but really what I want you to understand is now this, that if you integrate a function times a delta function, the result is it's just going to give you that function evaluated at the delta point. It's just going to give you that number. Example, minus infinity to infinity of delta 5 of t times t squared dt. So all I have to do this integral, it's so easy. I just plug 5 into t squared. I get 25. That's what we're saying is true here. And it works. Okay. So this is the important property of the delta function, how it operates under an integral. So just to summarize, and then we'll stop this particular video that is introducing this function. Let me just summarize. Here we are. The definition of the delta function in some sense, or at least sort of written as a function, is that it's infinity at this one point and 0 elsewhere. But with the property, and here are the two key things, how it works under an integral. If you integrate just the delta function from whatever to whatever, it doesn't matter, you get 1. And if you integrate the delta function times any other function, you get that function evaluated at a. You get f of a. Okay, so that really summarizes everything you need to know about this weird, quote, function, unquote. Remember, it's not really a function, but for all intents and purposes for us, it can act like one, and we just have to know these two properties to work with it.